Greetings, welcome to lecture number 21 on basic circuit theory. I am Razavi. Today we will talk about the situation where we have a driven circuit with an initial condition and see how we go about analyzing a circuit like that. And then we'll go over more examples trying to reinforce these ideas that we have been covering in the past few lectures. So our idea is to get comfortable with analyzing any first order RC circuit that's given to us with many different topologies. All right, but before we go there, let's take a look at what we covered last time. Last time we said that in many cases we draw a circuit like this where we have a constant voltage like a battery followed by a switch and then some sort of circuit. And we saw that in this case this is actually equivalent to apply a step here with a height of V1, because if I look at this voltage jumps from 0 to V1 after the switch conducts, and similarly this voltage jumps from 0 to V1 after we apply the step. So these two are equivalent provided that the initial condition on the capacitor is 0. Then we looked at this example where we had a current source with a switch and a parallel combination of R and C. And in this case, the switch turns off or opens at time 0. So the idea that switch no longer conducts and this current begins to flow this way. So if I sit here and look at this current is 0 before time 0, because this all flows through the switch, and then suddenly it becomes equal to I1 after time 0. So again, the circuit can be represented by a step at the input equal to I1 U of t. So you can see the similarity between having a step or having some sort of switching action. All right, and then finally we asked this question that I have a circuit which is driven. It has an input from outside, an independent voltage or current source, and then it also has some initial condition on the capacitor. So how do I analyze this circuit? All right, so today we'll talk about that, and we introduce two methods of analyzing a system like that. So we talk about the driven circuits with initial conditions. Okay, so method number one is very simple. We just write the circuit equation and differential equation and solve the differential equation with that initial condition that we have. So that's nothing strange. So solve the differential equation. Okay, should be lowercase here. Differential equation with the initial condition. Right? For example, if you remember for this type of circuit, R1, C1, and this is V in, and this is V out, right? So if you remember, after we solved the circuit and wrote the differential equation for it, to do so, first we found this current as I equals C dV over dt. Then we let that current pass through this resistor and give us a voltage drop from here to here, which was R1 C1 dV out over dt. And then we added this voltage to this voltage to get this voltage, right? So the equation we derived before looked like this: R1 C1 dV out over dt plus V out is equal to V in. Now, when we solved the circuit the first time, our assumption was that this initial condition was 0. So we just solved it by assuming that V in, for example, has reached a constant value. It's a step, right? There was a switch here and a step to a certain value, and we solved it, maybe by separation of variables. But if the capacitor has an initial condition on it when we start out, a non-zero initial condition, then we can write this differential equation still in this form, except that now we say V out at 0 plus is equal to sum V0. And V0 would be the initial voltage across C1. Because V out and the voltage on the capacitor happen to be the same in this problem, right, this example. So we just solve this differential equation subject to this initial condition. All right, we can do that. But there's another method, and sometimes that's easier. And that's use superposition. So do you remember what superposition says for a linear time invariant circuit? Superposition says if we have a system and it has an input X and it has an output Y, and we observe that when we apply one input X1, we get an output Y1. We apply another input X2, we get a corresponding output Y2, then the system is linear if it satisfies the following conditions. If I take alpha x1 and beta x2 and add them, alpha and beta are constant values. This is what we call a linear combination of two inputs. If we have a linear combination of two inputs going to the system, then the output should be a linear combination of these outputs. So the output should be alpha y1 plus beta y2. And it sort of makes sense, right? So if you double one of them, the corresponding output should also double, right? That makes sense. That's what the linear system should do. Okay, so now we apply superposition to this case. And what we do is we say, first, assume no input. So set the input to 0 and find V out for the initial condition. If you remember, we called this the natural response of the circuit, right? So we say, okay, we have no input here. If it's the voltage source, it becomes a short circuit. That's gone. We have an initial condition of the capacitor. We'll let the capacitor discharge or charge or whatever and see what happens, right? So that response is the response to the initial condition. We'll remember that. And the next step, we assume no initial condition. So assume no initial condition. And find V out in response to the input. Okay? So in a sense, I think of the initial condition as sort of an input, right? I say, just the way here we had one type of input gave us another output, and another type of input gave us another output, and we could combine these to get the final answer. Here we say the initial condition gives us an output. We remember that. The input without the initial condition gives us an output. We just add these two outputs to obtain the overall output. So in step number 3, add the two responses. Okay. Now, which method we use depends on the situation. Sometimes this is easier, sometimes it's easier. This is more intuitive, so if we can go with that, that's preferable. But sometimes it's actually more work, so we might as well go back with the original approach. So here's an example of how we handle initial conditions and inputs together. So example, we go back to that circuit here. So we have drawn that in different forms. Actually, let me still draw it as a step because that's easier to visualize. So we have a step, suppose this is called V1 U of t, and then I have R1, and then I have C1. The capacitor has an initial voltage on it, so we call that V0. And we are interested in this voltage as a function of time. All right. Okay, so there are many approaches to solving this problem. In fact, we could just eyeball it and decide what V out should look like, right? So let's try to predict the shape of V out. So V out as a function of time. How much is V out at time 0 plus? We know that the initial condition of the capacitor is V0. The current available to charge this capacitor is not infinity because there's a resistor here, right? So that means that the voltage on the capacitor cannot jump at time 0. So if it is V0 before time 0, it still has to be 0 after time 0. All right, it's fortunate that the voltage of interest to us happens to be the same voltage across the capacitor. That's not always true. But because we have the situation, we can readily say that the voltage at the cap, which happens to be V out, doesn't change with, in 0 time, so V out doesn't change in 0 time. V out is V0 and stays at 0, at V0. Okay, and then we apply a step. So this jumps from 0 to V1 at time 0. So what should happen? Well, let's go to time infinity and see what's happening. At time infinity, this voltage is V1, right? The difference between these two is V1, like a battery. And we're guessing that this capacitor voltage will be constant. So if this capacitor voltage is constant, the capacitor acts as an open circuit. It's an open circuit. It's gone, right? No current through it. If there's no current through the capacitor, there's no current through the resistor. If there's no current through the resistor, this voltage and this voltage are equal. So that's the output voltage at time infinity will be equal to this voltage, which is V1. So we expect that this goes towards V1. Right? So the only difference between this situation and the RC example we have seen in the past is that previously we started with the 0 initial condition. So we went like this, but now this time we go from V0 up to here. So that's our prediction of what should happen. But if we want to solve it exactly, we can, not a problem, right? So how do I do that? Yes, I could say, assume no input, all right? And find the output corresponding to the initial condition. So if I have no input, what does it mean? It means this is 0, it's a short circuit. I have a capacitor discharging to a resistor. So I can find that V out. So let's do that. So we say apply superposition. So step 1, no input. If there's no input, then we have just this, R1, C1, with an initial condition of V0. And this is a voltage source. When we set a voltage source to 0, it becomes a short circuit. So it's a short circuit here, and we're interested in this voltage. That's easy, right? One cap discharging through a resistor. So we say V out 1. I call it V out 1 because this is for step 1. V out 1 is equal to the initial condition times exp of minus t over tau. And tau is given by R1 times C1. That is the response due to only the initial condition. Okay? In step number 2, we assume no initial condition, but we now take into account the input. So we have no initial condition. Okay, if you want to draw the circuit, that's easy, right? We have a step here, V1 U of t. We have a resistor R1 and the capacitor C1. The capacitor starts with the zero initial condition. So that's easy, right? So we can, in this case, say V out 2, meaning for step number 2, this voltage starts from 0 and goes towards V1, this value here. So that would be V1, 1 minus x POV minus t over tau, and tau is equal to R1 C1. Okay? And now, step number 3, we just add up these two results. So step number 3, we say V out is equal to, see, we add up the results. So we add up the two outputs. So V out 1 plus V out 2. And that's equal to this quantity here, V0 x POV minus t over tau plus this quantity, V1 1 minus x POV minus t over tau. Does this whole thing take u of t? No, because V out was not 0 before time 0, right? So we can't multiply that by u of t. All we can say is that this is true for t greater than 0. Okay, so, but if you look at the circuit for a moment, you say, well, actually, I don't need to do any of this stuff. It's a first order system. And we have a general equation for a first order system, regardless of what it looks like. So we can say the alternative approach is, and it probably entails less work, so alternative approach, we say it's a first order system, and I can always write it like this, right? I can say y of t is equal to y infinity plus y0 minus y infinity x POV minus t over tau, right? So if I can find y infinity and y0 quickly, then I can definitely write the equation. All right, so how much is y infinity? How much is the output at time infinity? Well, we already predicted that, right? Because we said at time infinity, the voltage is probably constant. If it's constant, the current to the capacitor is 0. Capacitor is an open circuit. This voltage just goes right to the output, so the output will be V1. So we know that y infinity is equal to V1. And then y0 at 0 plus is how much? We decide that the voltage on the cap cannot change instantaneously because we don't have infinite current available. So the voltage on the cap at 0 plus is V0. So we have y0 is V0. So then we can just say V out of t is equal to y infinity plus V0 minus V1 x POV minus t over tau, and then tau is equal to R1 C1. So as they say, there are many ways to skin a cat, and you can see that we have this approach, which we didn't pursue here. We have superposition, or we have our general equation for a first order system. So depending on the situation, we can quickly pick one. All right, let's see how far we are with these examples. Okay, so I would like to go over another example. This example is a little tricky, so we have to be very careful about how we analyze it, but it's very useful. It's a great example of how all of these concepts come together. So let's change the color and go over another example. Okay, so in this case, we have a capacitor like so, C1, and we have a resistor like so, R1, and then we have a step at the input. We call this V1 U of t, and we are interested in this voltage, V out, And let's say that the capacitor has no initial condition on it. So I want to analyze the circuit. So you can see that the difference between this and the RC circuit we have analyzed in the past, something like this, is that previously we applied a step and we were interested in the voltage across the capacitor. Now we have applied a step and we are interested in the voltage across the resistors. It's the same circuit, right? So, but we are looking at the voltage across the resistors. And we want to analyze it. All right, so this takes a little work because things are tricky. We have to be very careful. We always go back to the principle that I is equal to C dV over dt. So if the current available to a capacitor is not infinite, the voltage on the capacitor cannot jump instantaneously. That's the most important one, right? The other one is, of course, if the voltage on a capacitor is constant, then the current of the capacitor is zero. So the capacitor acts as an open circuit. All right, so let's start from here. And again, before jumping to math, we want to qualitatively predict V out as a function of time, right? What does it look like? Okay, so let's do that. V out as a function of time. Okay, how much is V out before time 0? Before time 0. So V1 u of t is like this, right? So it goes from 0 to V1 at time 0. So before time 0, this is 0. There's nothing, there's no initial condition, there's nothing here, it's all dead, right? There's nothing in the circuit, all the currents are 0, all the voltages are 0, so V out is 0. All right, so we know that. Okay, so V out is 0 before time 0. Okay, how much is V out at time 0 plus? Meaning right after this input jumps to V1. So the voltage difference between these two was 0. Now it suddenly jumps to V1, right? That's the meaning of the step. So as soon as this happens, right after this point, how much is this voltage? Can we predict that? So that's the quiz of the day. I want you to think about it. This is the most critical aspect of the circuit, so we really have to understand it. I'll give you 1 minute to think about it. Okay, so how much is V out at time 0 plus? Well, what we know is that we are over here. So this plate of C1 has jumped to V1. Let's try to draw that a little more explicitly. So this voltage here has jumped from 0 to V1 with respect to ground, right? This is our reference point. All right, and then we have this resistor sitting here. So if the voltage on the left plate of the capacitor is V1 with respect to ground, how much is the voltage on the right plate of the capacitor with respect to ground? That's what we're trying to find out, because V out happens to be this voltage with respect to ground. Okay, so what we have to think about is what the capacitor wants to do or doesn't want to do. Because the current available in this loop cannot be infinity, right? This resistor limits the current, right? If you had infinite current, you would get infinite voltage, and we don't have infinite voltage anywhere, so that's not possible. Because the current through this loop is not infinity, the voltage on this capacitor cannot change in 0 time. All right, so let's write this step by step so that we can see what happens. So we say I is less than infinity, cap voltage can't jump. That means that VC1, the voltage across the capacitor at time 0 plus, has to be equal to VC1 at time 0 minus. Right? That's what it means. The voltage cannot jump instantaneously. Okay, so how much is VC1 at 0 minus? How much is the voltage across the capacitor before time 0? Well, that's easy, right? Because before time 0, this is 0. And the output is 0, right? This is 0, this is 0. So the voltage on the cap is 0. So that has to be 0. Okay, so here comes the key point. That is what a lot of students get wrong. So this voltage is V1. This voltage difference is 0. How much is this voltage? Has to be V1, right? So this point also jumps from 0 to V1. So the capacitor doesn't want this voltage to change. It's like a short circuit, right? So before time 0, the capacitor has 0 across it. After time 0, it still has 0 across it. The only thing is that one side of the capacitor jumped from 0 to V1. The other side of the capacitor also has to jump from 0 to V1 so that the voltage across the capacitor doesn't change. 0 minus 0 here, V1 minus V1 here. So the voltage at the output jumps from 0 to V1, from 0 to V1. Okay, if you don't understand this transition, pause the video, rewind, and study this very carefully. This is the key principle behind the circuit. Okay, so we have decided that V out has jumped to V1 at time 0 plus. And then or has jumped to V1, and that 0 plus is V1. Then what happens? All right, so let's draw the circuit again at 0 plus and see what it looks like. So at 0 plus, we have a battery here equal to V1. That's what the step means, right? It was 0 before and now it's V1, so it's a battery equal to V1. Then I have a capacitor, and then I have a resistor. And I want to see how V out changes with time. Past this point, how does it go? Okay, well, we have to understand what the circuit wants to do. We decided that when the input jumped to V1, the output jumped to V1. So if the output is at V1, is there a current through the resistor? Sure, there's a current of V1 over R1. So at that moment, there's a current through the resistor. And where does this current come from? It has to come from the capacitor. So it's coming from the capacitor. That current, I don't have room here, is equal to V1 over R1. Just at this point in time, right? You have V1 across the resistor, divided by the resistor gives us the current. Okay, this current begins to flow through C1. All right, and then flow from the battery, because this has to come from the battery, right? So this is going like this. So what happens to C1? We are passing a current through the capacitor with adding charge to the capacitor, right? If the current is flowing this way, it places positive charge here and negative charge here, right? So we collect positive charge on this side and negative charge on this side, right? If we have a capacitor and the current goes from top to bottom, then the top becomes more positive than the bottom, right? That's what it is. So this side becomes more positive than that side. Okay, so time goes by. The voltage on the capacitor wants to increase because we're passing a current through it. Now it becomes interesting. we have a voltage across the capacitor that's increasing with time, positive here, negative here. But this voltage with respect to ground is pinned to V1. This voltage is fixed. This voltage difference is increasing. What happens to V out? V out wants to go down, right? So that's another tricky point about the circuit. So I can write a KVL to show you. So let's write a KVL. Let's say minus V1. Let's call this VC1. Minus VC1. Plus V1 minus VC1 minus V out equals 0, right? Going up the potential, going down the potential, going down the potential, right? VC1. Okay. So what we see is that V out is equal to V1 minus VC1. V1 is the battery voltage, right? The step value. Okay. And VC1 itself, this voltage is increasing with time because the current places more charge here, more positive charge here, and more negative charge here. So if VC1 increases with time and V1 is constant, V out has to decrease with time. So V out will decrease like this. Okay? And the time constant associated with that should be just this product, right? We should prove that, but we would expect that the time constant is equal to R1 C1. So you can see that this little problem has so many interesting properties that seriously examine our understanding of how capacitors work, right? Okay, so now that we have found, we have predicted how V out changes with time, we can try to go ahead and solve the circuit. How do I solve the circuit? Well, there are different ways. Of course, you can write the node equation here if you want, and find the differential equation, solve it with the initial conditions that we have found. Or we can go back to this equation and try to use that. This is still a first order system, so I can try to use that equation, right? Okay. So let's try to do that. I have found the value of V out as 0 plus is V1. So that takes care of this guy here. For time constant, I know it should be R1 C1. Why? Because remember the method we had for finding time constant? We set the input to 0 and find the resistance that the capacitor sees. So we can find that. And we still have to find the y infinity. So let's just find these two values and then we're done. Okay, so let's try to find these. So first I want to find y infinity. How much is V out at time infinity? Okay, well what we see is that the current through this network keeps going down. You agree? Why? Well, because the voltage across the resistor goes down, right? If V out goes down, then V out over R1 goes down. So this current goes down. So the current begins to diminish at time infinity. If we have no current left at time infinity, the current times the resistor is 0. So V out eventually goes to 0. That's one way of thinking about it. Another way to think about it is that the maximum voltage we can have across this capacitor is this battery. So when the voltage on the capacitor reaches V1, V out has to reach 0. Okay, so Y infinity is 0. This happens way down, way out here, right? Okay, and we just need to find tau. Because we have this, we just have to find tau. Okay, how much is tau? So to calculate tau, we go back to our method for finding tau of any first order system. We said set the independent source to 0. So let's do that. I would have to draw it over here. Because the voltage source, when you set it to 0, it becomes a short circuit. And then we said, sit in place of the capacitor and see how much resistance we see. If you sit in place of this capacitor, how much resistance do you see? We see R1, right? Because they are actually in parallel. These two are shared, so we have a capacitor in parallel with the resistor, so the resistance seen by the capacitor is R1. So then tau comes out to be just R1, C1. And based on all of these that I have found, I can readily write the output, right? So I can say that the out of t is equal to the voltage at infinity. The voltage at infinity is 0, so 0 plus the voltage at time 0, and at voltage at time 0 we decided was V1 minus the voltage at infinity times exponent minus t over tau. So that is the voltage that we observed. Okay. Does this take a u of t? Yes, it does, because you can see that it's 0 before time 0. So we do have to multiply this by u of t. So this circuit is very interesting. When the input jumps from 0 to V1, the output has to jump because the capacitor doesn't want to change its own voltage. And now that the output has changed and R1 has a voltage on it, this much voltage, R1 begins to have a current. And that current is what's charging this capacitor up with positive on this side, negative on this side. And because this side is fixed, this side has to go down. This side goes down, it goes down until this voltage drops to 0. Now all of the battery voltage is sustained by the capacitor and the circuit is perfectly happy. So that's how the circuit operates. Okay, moving on to another example. Let's see here. Okay, so let's go to this example on the next page. All right. Okay, so this time we have a step like so. So V1 U of t. Then we have a resistor R1 and the capacitor C1. This part is something we are familiar with, so that's easy. But then to make things interesting, we have a switch and a resistor R2. And now we have the out here. And we want to analyze the circuit, assuming that this switch turns on at time equal t1. Okay, so the switch is open, it's not conducting before t1. T1 is greater than 0. And first we apply step. The step starts charging the capacitor C1. Maybe doesn't charge it completely. And then at some point in time, at T1, the switch turns on. It begins to conduct. And we would like to see how the out changes in all of this. All right, so again, we have a single capacitor, so things are quite easy. All right, so let's proceed. So, how much is V out for t less than 0? Before time 0, this switch is open, it's not conducting. So this resistor is sitting by itself, there's no current through the resistor, so V out is 0. So V out is 0 before time 0, is 0 before time t1. So it's just 0. Okay, all right. We probably have to give this a name, so let's call this VA, because VA and V out are not the same all of the time, so we just have to be careful. All right, so at time 0, something interesting happens. This voltage step is applied, so this point goes from 0, this difference, to V1. And the VA begins to change, but not V out, because the switch is still not conducting. So here's the situation. At time 0, We have our step coming in. So that's our input. And what we see is that VA begins to respond to that. So VA, which was 0 before, now assuming this capacitor has the 0 initial condition, it begins to respond. And it wants to go towards a value of V1. Just like what we've seen in the past, right? Okay, so that part is easy enough. But suppose that T1 is such that we don't allow C1 to charge completely. So again, we're going for some while, and then at this point in time, T1, that switch begins to conduct. And now we would like to see what happens. Okay, well, so we have reached a certain voltage for VA at this point T1, right? So let's just give it a name for now so that we have it. So we will call this V2. This is the value of VA at time T1, okay? Just so that we have it available. Now that the switch begins to conduct, what happens? Well, now we have a resistor here, and the capacitor. And the voltage difference between these two is a fixed value of V1. So as soon as we connect these two, at that moment, the voltage of the output has to be equal to the voltage of C1. Right? So let's try to plot V out as a function of time. So V out was 0 here, it's even 0 up to T1, right? Because the switch is not conducting. If the switch is not conducting, R2 has no current, no voltage, so the output is 0. Okay, at this point in time, what happens to V out? As soon as the switch conducts, V out has to become equal to the voltage across the capacitor. Right? These two. This is a wire, so these two are now in parallel. Can the voltage on the capacitor change from just before T1 to just after T1? No, because we don't have an infinite current available. So the voltage on the capacitor has to be the same value just before T1 and just after T1. So remember we called that V2? So at this point in time, V out jumps and assumes the value of V2. All right? So before that, V out was 0. The switch suddenly shorted these together, right? Shorted this part and this part together, so this voltage has to become equal to this voltage. And now the circuit is a new circuit, and this new circuit begins to go towards some V out, some final value, right? So let's draw the circuit after T1 to see what it looks like. So here I have a battery because this difference is now just V1, right? We are over here, so that's V1. And then I have R1, and then I have C1, and then I have R2. And I am interested in this voltage as a function of time. And at T1, the voltage on the capacitor is some value. We called it V2. So you can consider that an initial condition, and that's V2. So now from T1 on, I have to solve this circuit. This circuit has a battery on one side, an initial condition on the capacitor, and now it's going to go somewhere, right? V out will change towards some value. So we have to solve the circuit. All right, how do we solve the circuit? Well, remember, if we have a driven circuit with an initial condition, we can use superposition, or we can just sort of do it by inspection, right? We can solve it by inspection. Okay, so let's look at our time to make sure that we have enough time. Well, we're running out of time, but I can say that this is still a first order system. So I can say that V out is equal to this voltage at infinity. How much is that voltage at infinity? Well, this capacitor will be an open circuit at time infinity, so it's just the voltage divided result of these two. So that's V1 R2 over R1 plus R2, and then plus V0 How much is the voltage at time before the transition is made? Is V2, so right after the transition is made, minus V1 R2 over R1 plus R2 times x power minus t over tau, and tau in this case is something interesting. All right, so we'll come back to this problem next time, and we'll try to look at these values again to see where they came from, and we'll find the value of tau. I will see you next time.